Hi everyone, for those of you who don't know who I am, I'm Miss Donnan and I'm going to be taking you through the higher bonding and properties part of Unit 1. We're going to start by doing a very short recap of National 5 bonding and properties, just to make sure that we have the foundation knowledge there to build upon some of the higher stuff on top of that. There is quite a lot in the higher course for bonding, so the better our knowledge of the National 5 stuff, the easier it's going to be to transition to higher. So, 3 types of bonding that you should already know. We have covalent bonding, ionic bonding, and metallic bonding. Let's have a look at covalent first. So, back to very basics. A covalent bond is between non-metal atoms who share electrons to obtain a full outer shell of electrons like a noble gas. What holds the bond together is the mutual attraction between the positive nuclei, so the nucleus is positive because of the protons, for the shared pair of electrons. Remember, opposite charges attract, so the positive nucleus is attracted to the negative electrons. A molecule is a group of atoms which are covalently bonded together, and there are 4 different shapes of these. Now, you do have to be aware of the 4 different shapes and their names. So, we've got linear, where there is usually only one bond between the atoms, but I have put in an example of one which is still linear, but there are 2 bonds. It is oxygen, O2, and it has a double bond. Nitrogen, N2, with a triple bond would still be a linear molecule. Most of the time though, you will see these with only one bond. For example, HCl has only one bond in the middle and it's linear. If we have 2 bonds, then we're looking at something which is called angular. So it has 2 bonds to the central atom. In this case, your example is water. Trigonal pyramidal is the next example where we have 3 bonds to the central atom. You have ammonia here, and we also have some wedge and hash bonds to show that the H's come out to the front and kind of to the back as well. These are 3D molecules, they're not things that we can just press flat on the table, so it's useful for us when we're trying to draw these as 3D to have a bond that comes out to the front and one that goes to the back. Tetrahedral is the last one, and it has 4 bonds to the central atom, which happens to be carbon here. So we have methane at the end, and it is a tetrahedral with 4 bonds. So as I said, you have to know all 4 names and all 4 shapes. Covalent structures can appear in 2 different ways. They can be discrete molecules or networks. And these are completely different structures, so we have to have a good understanding of these. Discrete molecules, firstly, they can be solids sometimes, but mostly they are liquids and gases at room temperature. That's because they have very low melting and boiling points. So by the time it gets to room temperature, they have already melted into a liquid or boiled into a gas. Some examples you have at the bottom there are carbon dioxide, silicon dioxide, and water. Make sure you have some go-to examples for discrete molecules and networks. Now, why do these have low melting and boiling points? Well, because they exist as little bits of molecules, they are held together by very strong covalent bonds on the inside, but between the molecules they are held together by very weak forces of attraction, and that's why their melting and boiling points are so low. It doesn't take a lot of energy to break these. Networks are the opposite. Networks are held together in all directions by covalent bonds. They don't exist as molecules which are kind of attracted to each other. It's a big, giant lattice structure which is made up entirely of covalent bonds. So they have extremely high melting and boiling points because of this. They're always solids at room temperature. That's because it takes such a high amount of energy to break the covalent bonds. And your examples for this are diamond, which is made up of carbon atoms, silicon dioxide, which is sand, and also for an example you could have carbon in the form of graphite, which is your only covalent structure which conducts electricity. That's your one kind of exception to the rule. So, covalent structures can exist as discrete molecules or networks. You have to know some examples of each and also be able to explain the differences between these. Ionic bonding then, we are now talking about transferring electrons rather than sharing, and this is between metals and non-metal atoms. Metal atoms always lose electrons to become positive ions, and non-metal atoms always gain electrons to become negative ions. This obviously produces oppositely charged ions. We all know that opposite charges attract each other, and this forms an ionic bond. Your definition for an ionic bond is the electrostatic force of attraction between oppositely charged ions, and you have to know that. There is a wee diagram here that shows what that might look like. The ionic lattice is the only structure that we find ionic compounds in. It's a regular repeating structure which is made up of your positive ions and negative ions which surround each other. It conducts electricity when molten, so melted, or in solution, aqueous, but never when solid. Why is that? Because when the ionic compounds are solid, the ions are locked in the lattice and can't move. Electricity, remember, is a flow of charged particles, so where there is no flowing of charge or no moving of charge, there can be no electricity. So ionic compounds dissolve in water easily. When they do this, the water molecules break up the lattice, so they break the ions apart, and then they are on their own and free to move wherever they want. So, when the ionic lattice is dissolved in water, if an ionic compound is aqueous, it does conduct electricity. The other scenario where the ionic lattice is broken is if it is molten, which just means you heat the ionic compound up to such a high temperature that the ionic bonds are melted and the ionic lattice breaks apart. That situation would allow ions which are free to move as well and carry the charge. So in both aqueous and molten scenarios, ionic compounds do conduct electricity, but they don't conduct when solid. Last type of bonding is metallic bonding. In this type of bonding, electrons are said to be delocalized. Now, what that means is they do not belong to one particular atom as such, but what they do is they move around the outside, which leaves the atoms as positive ions because they're missing one of those electrons. So this sometimes is referred to as a sea of delocalized electrons, and what happens is the electrons can move between each of the positive ions, which creates the possibility for carrying charge. That's why all metals conduct electricity. Metals are solids at room temperature, and they consist of these positive ions being packed quite closely together, and they are also in a lattice structure, but the difference is this is a metallic lattice. So it's made up of these positive ions and delocalized electrons. And what the metallic bond is the electrostatic force of attraction between the positive ions and the negative delocalized electrons. So quite similar to ionic bonding, but not quite. And there are subtle differences you have to remember. You have a summary of properties on page 1 of your higher notes. I'd like you to have a wee look at that, please. See if I can move this. So we have covalent molecules are between non-metal elements. They have low melting and boiling points, and they never conduct electricity. Covalent networks are generally between carbon, boron, and silicon. They are very, very high melting and boiling points and never ever conduct, except the one instance, which is carbon in the form of graphite. Ionic bonding has a lattice structure which consists of metal and non-metals. Their melting and boiling points are also very high, and they only conduct when aqueous or in solution, never solid. Metallic bonding occurs again in a lattice structure, but it's only between metal atoms. They have high melting and boiling points, but it's quite a varied range, and they always conduct electricity. So you can go and highlight this table in your notes if you want to. It's on page 1 of your higher bonding notes. But I would like you to now go and complete the bonding and structure quiz and the fill in mind map. So this is just a kind of a week to recap all of our Nat 5 knowledge, get it up to scratch before we start going on to the higher content. Thank you for watching.